The sun is one of humanity's primary sources of life, perhaps even the most important one. But where was this star, our main source of life, actually born? Recent studies give us a remarkably clear answer to this question, but to truly understand the situation, we naturally need to dive much deeper into the details. Today, we're going to explore where our star was born, the research conducted on this topic, and crucial concepts regarding general star formation. But before we get started, if you enjoy videos like this, don't forget to subscribe to the channel, like the video, and share your thoughts in the comments for future video ideas. First of all, we must realize that if we as humanity want to understand the structure of the universe, there is a critical question we need to ask, and that is, where and under what conditions was the sun, the main protagonist of the star system we inhabit, formed? This question isn't just a matter of astronomical curiosity. On the contrary, it reveals essential insights into planetary formation, chemical evolution, and ultimately the emergence of living beings like us. The sun's birthplace is one of the most vital factors determining the solar system's initial chemical composition, isotope ratios, matter distribution in the protoplanetary disk, and even Earth's internal structure. For this reason, in modern astrophysics, research and analysis regarding the origin of the sun represent an immensely complex field of study at the intersection of star formation theories and galactic dynamics. Today, we know for a fact that our sun formed 4.6 billion years ago, and thanks to radioisotope dating methods, we were able to learn this with nearly zero margin of error. In particular, the decay rates of short-lived radioactive isotopes found in meteorites played an active, one might even say key role, in calculating the formation time of the solar system. However, despite knowing its age, pinpointing the sun's birth location within the galaxy remains exceptionally difficult for us. In fact, since the advent of modern astrophysics, this has been one of the hardest things to determine about the sun. The primary reason for this is that the Milky Way is not a static structure. Contrary to popular belief, the Milky Way is not a quiet, tranquil, and static environment. Rather, it is a constantly evolving, dynamic, and highly complex system. Stars within the galactic disk exhibit a movement called differential rotation, meaning that different regions of the galaxy rotate at different angular velocities. This might sound confusing to many people at first, but with a little imagination, it's easy to grasp just how magnificent these movements across the Milky Way really are. It is precisely this weird differential rotation that causes stars to drift hundreds or even thousands of light years away from their birthplaces over billions of years. Furthermore, spiral arm dynamics, gravitational interactions, and encounters with molecular clouds cause deviations in stellar orbits. Therefore, calculating a star's past location is not as simple as tracing its trajectory backward. There are numerous parameters you must consider and analyze, requiring the solution of a high-dimensional dynamical system. In other words, contrary to what some might think, saying, the sun moves this many kilometers per year toward that point, so over 4.6 billion years it must have come from this direction, is perhaps the very last thing you could say on this topic. In recent years, high-precision astrometric data provided by the European Space Agency's Gaia mission has made these calculations significantly more feasible. Gaia mapped the galaxy in 3 dimensions by measuring the positions, parallaxes, and proper motions of billions of stars with micro-arcsecond precision. This data allowed for the determination of stellar velocity vectors, enabling simulations of past orbits using galactic potential models. These backward time integration methods have been used to determine which regions the sun occupied in the past, where it traveled, and where it most likely formed. I want to draw your attention here. Even with all this, we still cannot definitively state that it formed in one exact spot. One of the most striking findings emerging from these analyses is the sun's association with a massive molecular gas structure located in the Orion Arm, known as the Radcliffe Wave. The Radcliffe Wave is a galactic-scale, filament-like structure spanning approximately 2.7 kiloparsecs, or roughly 9,000 light-years, in length. If you'd like, I can make a detailed video about this wave as well. Don't forget to drop your thoughts in the comments. Anyway, this structure features an oscillating geometry relative to the galactic plane and exhibits distinct continuity in both position and velocity space. The discovery of the Radcliffe Wave was made possible through 3-dimensional analyses of Gaia data, revealing that many star-forming regions previously thought to be independent were actually parts of a single vast structure. This alone is one of the greatest recent discoveries because prior to this, we believed that independent stars formed in entirely different regions under completely different conditions. Yet thanks to this discovery, we learned that they actually formed within different pockets of the very same region. much like siblings growing up in different rooms under the same roof. The molecular clouds contained within this structure are the primary stages for star formation. Molecular clouds are defined as regions composed mostly of hydrogen molecules, characterized by extremely low temperatures and extremely high densities. Within these clouds, a process known as Jeans instability takes place. According to the Jeans criterion, when the mass of a gas cloud exceeds a certain critical threshold, the internal thermal pressure can no longer withstand gravity, causing the cloud to collapse under its own weight. This collapse leads to localized density increases, eventually culminating in the formation of young stellar cores called protostars. Over time, these cores grow by accreting surrounding matter, and once nuclear fusion ignites, they transform into main-sequence stars. The significance of the Radcliffe wave stems not only from its massive size, but also from the fact that it is an area where this star formation process occurs intensely. Well-known structures like the Orion Nebula, the Perseus molecular cloud, and the Taurus star-forming region are all parts of this wave. Stars at various evolutionary stages can be observed within these regions, offering us a natural laboratory to study the temporal evolution of star formation. And scientists couldn't ask for anything better. Under normal circumstances, scientists attempt to artificially test phenomena they cannot directly observe in space by recreating near-realistic conditions in earthbound laboratories. In this case, however, scientists are getting exactly what they need right in nature. It is believed that our sun was born in such an environment, underwent a similar process, and was initially part of a dense star cluster. Another crucial clue regarding the sun's birth environment is the presence of short-lived radioactive isotopes in the solar system. Isotopes like aluminum-26 and iron-60 in particular are produced during supernova explosions, and because of their short half-lives, they must have been injected into the solar system shortly after its formation. This proves the presence of a nearby supernova explosion right in the environment where the sun was born. Such explosions can compress surrounding molecular clouds to trigger star formation, while simultaneously injecting heavy elements into newly forming stellar systems. In essence, our sun still carries the traces of a supernova explosion from its natal environment within the system today. In this context, active star-forming regions like the Radcliffe wave serve as ideal environments for these processes to unfold. Our star's galactic orbit is another parameter that demands close examination. The Sun orbits the center of the Milky Way in a cosmic year lasting roughly 230 million years. Since its formation, the Sun has completed around 20 galactic orbits, interacting with spiral arms, passing through varying density regions, and experiencing minor orbital deviations due to the galactic potential. Therefore, it is entirely expected that there would be a difference of a few hundred light years between the Sun's birthplace and its current location. Indeed, simulations indicate that the Sun has migrated about 500 light years away from its birth region. Another phenomenon catching scientists' attention is the remarkably dynamic nature of the Radcliffe wave. In other words, this structure exhibits behavior that seems almost paradoxical within the Milky Way. It has shown us that it is not merely a static gas filament, but a wave pattern oscillating through the galactic disk. Unfortunately, we still don't fully know the exact cause of this oscillation. Mechanisms such as fluctuations in the galactic gravitational potential, spiral arm interactions, or a past galactic collision are currently scientists' leading hypotheses. Large-scale structures like this play a vital and critical role in galactic evolution, directly influencing star formation rates. The fact that our sun was born in such an environment can affect not only the chemical, but also the dynamical properties of the solar system. For instance, the gravitational pull of nearby stars close to the protoplanetary disk around the early sun could disrupt the disk structure or accelerate planet formation processes. Additionally, radiation and supernova effects within dense star clusters play a direct role in protoplanetary size distribution, orbital architectures, and chemical compositions. Furthermore, to truly understand the sun's birth environment on a deeper level, we must look into the physical mechanisms of star formation itself, because the birth of a star is far more complex, larger in scale, and involves vastly more physical processes than a simple gas cloud collapsing. Molecular clouds are recognized as the primary birthplaces of stars and galaxies, and their internal structures are governed by turbulence, magnetic fields, and radiative processes. Contrary to popular belief, these clouds are not homogeneous. Instead, they possess fractal-like structures filled with density fluctuations. Turbulence plays a dual role here, acting as a mechanism that both triggers and inhibits star formation. On one hand, it compresses gas to create localized density spikes. On the other hand, it supplies kinetic energy to delay collapse as much as possible. This is where Jean's instability comes back into play. While Jean's instability is considered the starting point of star formation, this criterion alone is insufficient in real astrophysical environments because molecular clouds are not merely balanced between thermal pressure and gravity, they are also subject to magnetic pressure, turbulent pressure, and external radiation. Consequently, modern star formation theories rely heavily on magnetohydrodynamic simulations. These simulations account for the interactions between ionized gas components and magnetic fields, illustrating how the collapse process is shaped. While magnetic fields allow gas to collapse more easily along certain axes, they create resistance along others, giving rise to filamentary structures. The existence of colossal filaments like the Radcliffe wave demonstrates that such processes are active even on galactic scales. When the collapse phase begins, the gas cloud's angular momentum is conserved, causing an accretion disk to form and rotate around the central protostar. This disk is the environment where planets will eventually form. The transport of angular momentum is a critical challenge at this stage, as momentum must be transferred outward for gas to accrete inward toward the center. Viscosity, magnetic fields, and spiral density waves within the disk play essential roles in this process. In particular, magnetic braking mechanisms regulate the disk's rotational speed, allowing the collapse to continue. During the protostellar phase, central temperature and pressure rise steadily. When temperatures reach several million Kelvin, nuclear fusion ignites through the fusion of hydrogen nuclei. This moment marks the star's entry onto the main sequence. However, before reaching this milestone, the young star generates powerful stellar winds and jets. These jets aid in angular momentum transport and clear out surrounding gas, allowing the star to emerge more clearly. This process is also supported by observational evidence. Specifically, Herbig-Haro objects are the observable results of these jets interacting with molecular clouds. Considering that the Sun underwent these very processes, its birth environment must have possessed similar physical conditions. As mentioned earlier, such processes occur frequently in dense star-forming regions like the Radcliffe wave, strongly indicating that the Sun was likely born within a star cluster. Modern observations reveal that the vast majority of stars do not form in isolation as once thought, but rather in clusters. Over time, these clusters disperse, scattering their stars throughout the galaxy. It is believed that the Sun was part of such a cluster and eventually drifted away. At this point, the concept of solar siblings emerges, bringing new debates to the astronomical world. According to this theory, if the Sun was born inside a cluster, there should be other stars born from the very same gas cloud. These stars would initially share similar chemical compositions and ages. However, over billions of years, galactic dynamics pulled them apart. Today, astronomers use a technique called chemical tagging to locate these solar siblings. By analyzing stellar spectra, scientists determine elemental abundances to identify stars with matching chemical signatures. If a star carries the exact same chemical fingerprint as the Sun, the likelihood of it originating from the same birth cloud is extremely high. Through these studies, a few candidate solar siblings have been identified, though definitive proof remains elusive. This is because galactic mixing gradually alters the chemical and dynamical characteristics of stars over time. Furthermore, supernova explosions and the evolution of the interstellar medium can disrupt chemical homogeneity. Therefore, tracking down the Sun's long-lost siblings requires a multi-dimensional analysis incorporating chemical, kinematic, and age data. In fact, according to some astronomers, identifying these solar siblings is even harder than pinpointing the exact birthplace of the Sun itself. Additionally, the Sun's galactic journey is of great importance. The Sun didn't just drift away from its birthplace, it also oscillates vertically up and down across the galactic disk. These movements occur perpendicular to the galactic plane, with a period of roughly 60 to 70 million years. Such oscillations push the Sun through varying density and radiation environments. Some research suggests these galactic crossings might correlate with biological evolution and mass extinctions on Earth, though this topic remains debated. The solar system's interaction with the interstellar medium is equally crucial. The heliosphere surrounding the Sun is in constant interaction with interstellar gas and dust. If the Sun passes through a dense molecular cloud, the heliosphere could compress, increasing the cosmic ray flux reaching Earth. This, in turn, could impact atmospheric chemistry and climate. Massive structures like the Radcliffe wave stand out as regions where such interactions are highly likely to occur. In conclusion, guys, our Sun most likely came to life in a region within in the Radcliffe Wave, close to a supernova explosion, and then embarked on a journey spanning billions of years. While it isn't known with absolute 100% certainty just yet, scientists argue there is about a 95% probability that this is how it happened. I hope you enjoyed the video. If you liked it, don't forget to hit the like button, subscribe to my channel to support me, and leave a comment with your ideas for future videos.